My name is John Erwin. I want to thank you and the hosts very much for the opportunity to speak in front of you today. I'm going to talk about something very different than what the past two speakers spoke about. I'm going to focus just on the plants themselves. And I'm going to talk about the impact of the environment on vegetable crop yield and nutritional value in controlled environment systems. And I'm going to be speaking to you from the University of Maryland. Just as a quick advertisement, my department includes plant science, horticulture, agronomy, turf, forestry, agriculture extension, landscape architecture, and fermentation science. We have 43 faculty and lecturers, 66 grad students, and 22 postdocs. The university itself has 40,000 students. And we're located on the East Coast in the small state of Maryland, which is one of the first states in the United States, and also one of the densest and also one of the richest. And we're right in the area between Washington, Philadelphia, and New York. Where much of the state includes the Chesapeake Bay, which is the largest bay in the United States. And something we're noticing being quite near all these major metropolitan areas is that, of course, we have a dramatic increase in the interest in controlled environment agriculture. We obviously consume a lot of vegetables in this area, so the interest in this area has grown tremendously. And I'm going to talk about three different areas. I'm going to talk about just what we're noticing in temperature, light, and CO2 effects on yield of controlled environment crops, how the environment affects the nutritional value of greens, and then also issues around food safety and future areas of research that we're looking into. So these are some general concepts. So this is a general concept, and this applies for vegetable crops as well. Unfortunately, this is in degrees Fahrenheit, but we see around 10 degrees C, we have a base temperature, and as the temperature increases, and this is average daily temperature increases, the leaves per day on leaf unfolding increases up to, in many cases, around 30 degrees C. Now, this is quite different for some of the leafy green crops, such as the lettuces and so forth, which have a different impact, where they have a maximum temperature that is lower. But I would come back to this and just note that when you go above a certain temperature, the leaf unfolding decreases, which is significant in vegetable crops. If we look at fresh weight gain per day, you can see with arugula, mizuna, mustard, and kale that the optimal temperature is around 20 degrees Celsius or 68 degrees Fahrenheit. So you can see it's quite a bit lower. And again, this is related to fresh weight gain per day. So it's a different unit that we're looking at. If we look at some specific crops to show you the dramatic difference in how they respond to temperature, if we look at photosynthesis on the left and temperature on the x-axis, you can see that the chard increases, photosynthesis increases dramatically from 2 up to 8, or quadruples as you go from 10 to 28 degrees Celsius. In contrast, if you look at kale, you'll see that photosynthesis is optimized right around 16 to 17 degrees Celsius. And as you go warmer, photosynthesis actually decreases. And if you look at an experiment where we moved plants between chambers, we had chambers held at 10, 15, 20, 25, and 30, and then we moved plants between these chambers every day and every night to get 25 different day-night temperature combinations, you'll see that in this case, with red rush and kale, that we have optimal temperatures both day and night between 15 and 20 degrees C with respect to fresh weight gain on 4 leaves. If we switch gears and look at light, you heard about light and LEDs a moment ago. When we are at lower light intensities or radiance, we also often say this is light limited. And as was suggested in the last talk, when you get to a higher light intensity, you have a plateauing of photosynthesis. But in many cases at those intensities, we are CO2 limited. And I'll come back to that in a moment. With one of the largest lettuce producers I work with in the world, one of the first things we did actually was to start by looking at different lettuce varieties. And these are different kinds of romaine varieties and some newly bred varieties. And on the bottom is photosynthetically active radiation, and on the right is photosynthetic rate. The first thing I want you to notice is Arroyo, which was the most common romaine grown in the United States, has a maximum photosynthetic rate of around 20, which is the yellow line. If we go to the new experimental variety, 16925, you can see that very same conditions, resulted in a photosynthetic rate of 30. So a 50% gain in photosynthetic rate alone, just from picking varietal selection. So with any company I work with, the first place we start is in variety selection, because it can have a profound effect on yield without impacting any input costs environment. We've done a significant amount of work on different types of green species. On the top, you see an irradiance response curve where we have increasing radiance, and then and on the y-axis is photosynthetic rate. And you can see that the shape of the curves are very much similar. However, the plateaus are at different places with many of these greens. But you can see once you get up to 800 micromole, when you get above it, you have some incremental increases. In some cases, it's very small, and others you have a continued increase in photosynthesis, which is directly related to yield. Below, you'll see CO2 concentration. When I was in graduate school, CO2 was 332 parts per million. I'm dating myself, because now ambient CO2 is around 405 parts per million. But you can see that increasing CO2 from either 300 or 400 higher is a significant and important way to increase photosynthesis. And in many cases, this is far more economical than adding lights. So it is common in the U.S. for producers in greenhouses to increase their CO2 levels to 800 to 1,000 parts per million because of this. Now, something that's interesting that's happening as the CO2 level increases, and just to go back to the when I was in graduate school versus now, that's a 22% increase in CO2, which is going to give you a significant increase in yield for the same area. Often people don't discuss this, but if you go to a forest or our yards, that 22% increase in CO2 is a benefit to plant growth. However, this is a paper published in Nature in 2014. What this shows clearly is that under these higher CO2 situations, that the nutritional value of some of the most important crops that we grow is decreasing. So we don't have much input or work on this as far as greenhouse crops. Now, something that's noted is that in a closed system, and this really applies for vertical farming systems, that when we have a closed greenhouse, a single hour under low, medium versus high light can decrease the CO2 dramatically in the greenhouse. And in many cases, in some of these controlled environment systems, the CO2 levels may be limiting, particularly if the plant material is stacked. You can see 1 hour it dropped from 400 down to 340 parts per million under medium light conditions. Something that people did not have that we did some work on is vapor pressure deficit. Often people are trying to identify the optimal vapor pressure deficit. We did many different environments and looked at the impact of vapor pressure deficit on photosynthetic rate, and we found that the optimum is between 0.7 or 0.8 and 1.2. And this is not published yet. If we shift gears and look at the solution temperature that people are using to grow their crops, we looked at different herb crops, and this is the leaf fresh weight, which is essentially the yield of herbs. And I'll just note that dill has an optimum solution temperature of 25 degrees C, whereas basil, which is the red line, has an optimum solution temperature of 30 degrees C. So in some cases, increasing or decreasing solution temperature can have a significant impact on yield without increasing light or temperature. And we find in some cases in greenhouses, when we have pots in a greenhouse, that we're losing roots. This is tomatoes. And when we have a temperature that is right around 28 degrees C, our pot temperatures can easily get to 50 degrees C, thus killing roots if they're in a black pot. So we're looking at aerated or white pots for any containerized production in greenhouses of vegetables. Environmental effects on nutritional value. There's a desire to make the most nutritious possible greens when producing these systems. And I think there's a real opportunity to advertise to this, just to show you a difference in nutritional value between a carotene level in tomato between 20 and 30 degrees C greenhouse. If we look at lycopene, at 20 degrees, you can notice it's 40.5, and at 30 degrees, it's 1.1. Huge difference. And I think the controlled environment ag industry really has an opportunity to advertise more about the nutritional value that they provide. This is an old graph, just basically showing lycopene concentration in vine-ripened tomatoes under low EC versus high EC, and EC is electrical conductivity or nutrition. And I think we all appreciate that if we feed or fertilize more, that our yield is going to be lycopene content, or the nutritional value of the food has increased, and that's in fact the case. When we went to a conventional grocery store and then went to an organic co-op in the same area and looked at the same mix, we went ahead and measured the vitamin C content of these two different bags in the two different sales systems. And I note that the conventional grocery store, we had a vitamin C content of 11.5 milligrams per 100 grams. And notice under the organic co-op system that we had over 20 milligrams per 100 grams. So significantly more vitamin C in the organic co-op. What's the difference between the two? In many cases, the organic co-op is more locally grown product that is often closer to the point of sale. We did research on the impact of time from cutting on vitamin C content, because we had some experiments that were farther out in the state. We wanted to see the impact of a single day. And this just shows that by day 8 in Mizuna, that the vitamin C content has decreased to almost zero. So this brings home the fact that when we are producing crops in California on the other side of the United States, shipping them across the country, and then selling them 5 to 7 days later to consumers on the eastern side of the United States, for instance, where I live, that in many cases, you may have very little nutritional value left of certain nutrients, vitamins in particular. We did a study where we looked at opportunity crops that produce managers identified and restaurateurs, and how to produce those in our area. And again, we'd use different day-night temperature combinations. And this is a graph showing the effect of, or the impact of temperature on kale vitamin C content. And you can see that clearly the vitamin C content was highest between 15 and 20 degrees day temperature. Interestingly, also 20 to 25 degrees night temperature. This was quite different from iron. If we look at some of the same experiment with iron content increased with increasing night temperature alone. Day temperature had essentially no effect on iron content, which was quite interesting. And then we have a group of nutrients, calcium and potassium fit in this group, that when you have a high day or a 30-degree day combined with a cool night, a 10 to 15-degree night, that you have the highest potassium and calcium content in those cases. So we can start putting together these different temperature regimes to come up with the best temperatures that exist for each different greens crop that will provide the optimal nutritional content in that crop. So it's quite easy to do. Interestingly, also photoperiod has an impact. Now, kale is not photoperiodic, yet if we grow under short days and long days, we'll note that under short days, our vitamin C content was higher in kale at each light level that we looked at. So it was kind of interesting. We didn't really understand that because logic would say that the longer the day, the higher the vitamin C content, but that was not the case with kale. Also very interesting, and I think we're going to be doing more work in this, is we compare different media in the same greenhouse with greens production. We have conventional media on the far right, and we looked at vitamin C content. Notice under PL, we inoculated the media with poultry inoculum. So this is a solution, a leachate from poultry litter, and then we washed that out. And so the nutritional content was the same between these treatments, fertilized the same, grew the plants in the same bench and the same greenhouse. And notice that the poultry litter, for whatever reason, and the only reason we could attribute to this is biological activity, that it had 16 for vitamin C content, and conventional media had 4. Very, very different, and we don't understand this. Last thing I'll talk about is issues around food safety. Hopefully I'll have a little bit of time for questions. We talked about those different day-night temperature combinations. I want to point out that when you have a very high day combined with a very cool night, that the nitrate levels exceeded the EU safety standard. Now, in the United States, if you go to California, it was mentioned before, We grow quite a bit of our lettuce in California. And in fact, the temperatures there are between 25 and 30 degrees during the day and 10 to 15 at night. We likely are producing and consuming a significant amount of lettuce with high nitrates, which is detrimental to human health. The other thing that we're finding is that we're starting to appreciate more and more is the importance of calcium for a variety of different reasons, okay? One of the things we're looking at doing with calcium is we apply calcium chloride, which is, we would call that commonly road salt here. And then we're finding that it provides a couple benefits. One is that we're actually getting increased yield in many cases with calcium chloride application. In addition, when you apply calcium chloride, you actually inhibit bacterial and fungal diseases. And so it actually improves food safety. So we're looking at applications of calcium chloride in particularly microgreen production. As far as future areas, plants don't have vocal cords or eyes. When they're attacked by insects or diseases, they give off volatile compounds and tell adjacent plants that they're being attacked, so those adjacent plants can turn on their defenses. There's a gas chromatograph profile of an uninfested ulmus, which is a tree, and the forestry people are way ahead on this topic. And if the same plant is attacked by a beetle, you can see the increase in peaks coming out of the leaf. These are all different gases of different kinds. One of the gases is called methyl jasmonate, and it's a common compound actually in perfumes. In this case, we did an experiment where we put 11 aphids onto watercress and then came back after 11 days and counted, 8 aphids, and then came back after 11 days, counted the aphids. So you can see untreated plant, we went up to 22 aphids after 11 days, but the one with methyl jasmonate, we actually went down, showing that one exposure to methyl jasmonate gas turned on defenses and reduced aphids. So if we switch gears just a little bit, look at flowering, I will just mention to you that a 2-hour, 35 degrees Celsius exposure we've found on greenhouse crops and with lettuce, it can decrease the maximum photosynthetic rate by over 50%. And that exposure takes 3 days for the plant to recover. And when we look at that, we're finding that it's because the stomates on the bottom of the leaf are closing. And when that occurs, photosynthesis stops. And we're finding that that's associated with ABA, and we're actually looking at abscisic acid. We're looking at how we may alter abscisic acid molecularly to increase heat tolerance of some of these crops. There's a broader group at the University of Maryland working on how to molecularly modify plants to improve crops. And I'll just mention this one example, and it does apply to the vegetable industry. But fusarium is a common disease called wheat scab in Maryland. Worldwide, it affects wheat significantly. We have a faculty member who was able to take out a scab resistance gene out of wheat and effectively put it into Arabidopsis, a dicot. And on the far right, you'll see a normal Arabidopsis leaf, and on the bottom, you can see fusarium infection. And on the two to the left, you can see those transformed Arabidopsis, and then you can see they're effectively resistant to fusarium. Fusarium is the largest problem in tomato production, and this is why we graft tomatoes to graft them onto a fusarium-resistant rootstocks worldwide. So we're looking at developing new rootstocks that may be very fusarium-resistant, particularly helpful in Africa and the United States. And we have new CRISPR system that we've developed, CRISPR-Cas9 Act 3. And in this case, you can see 2 plates, and on the right, a gene called FT has been turned on in those plants to continuously flower. So we think continuously flowering or continuously not flowering have applications in vegetable industry that are significant. So with that, I don't know if I have any time left, but I'd be happy to answer any questions you may have related to the green or environmental effects on plant nutrition. Thank you.